Hello everyone, welcome to the course Expansive Soil. This will be the 17th lecture of the module 6, which will be the behavior of the expansive soil, and today we will be learning about the thermomechanical hydraulic chemical behavior of expansive soil. In previous class we learned about the different behavior of different type of clay such as montomonite, illite and kaolinite. We learned about the swelling, the shrinkage and the compaction characteristics of different minerals, and today we will be learning about the swelling, the hydraulic and the compressibility behavior of montomonite, illite and kaolinite. In the last class we learned about the different mechanism which controls the different behavior of the soil. Say for example, in montomonite, the diffuse stable layer or the repulsive forces generally controls its behavior, whereas for kaolinite the clay fabrics or the attractive force generally controls its behavior. So, in the continuation of the previous class, today we will look into the other factors or other properties of the clay minerals. Before going into the details, first I would like to explain you about the clay and expansive soil matrix in a sand and expansive soil mixture. Say for example, in this case we have taken one non-expansive soil such as sand grains, and we have taken one expansive soil such as montomonite. Here we can see that these are the sand grains and these are the individual montomonite particles. Here we can see between the different sand grains we have a large number of void space or pore space. So, these large interaggregate pores are known as the macropores. Then we can see over here there are different number of clusters of montomonite particles are there. In each cluster there will be n number of different unit layers of montomonite will be there, and each cluster will be made of n number of montomonite particles, and in between this cluster or in between these montomonite particles we can see the small voids. These small voids are known as the micropores or intra-cluster pores. Here you can see in this diagram, these are the individual unit layer of montomonite particles, and in between there is a space which is known as intra-cluster pore space or the micropores. Here this is the individual montomonite particles, and here you can see between the two unit layers we have some space over here. So, that is occupied by exchangeable cations and water molecules, and this space is known as interlaminar pore space or ILP. So, generally when we talk about the different type of voids present between a sand or a non-expansive soil and an expansive soil matrix, we can get three different type of pore space. One is known as interaggregate pores, that is macropores. Then we have the intra-cluster pores, that is known as micropores, and we have the interlaminar pore space, that is the space between two unit layers of the montomonite particles. If we look into the hierarchy of these pore spaces, for a non-swelling state or a less swelling state, generally the interlaminar pore space are smaller. That will be followed by the intra-cluster pore or micropores, and that will be followed by the macropore or interaggregate pores. So, generally for a less swelling state, the interlaminar pores are smaller and the biggest one will be the interaggregate pore space. But once the soil starts to swell, or when this individual particles or individual montomonite particles starts to absorb moisture, then this interlaminar pore space will increase. As the interlaminar pore space will increase, the cluster size also starts to grow. As the cluster size starts to grow, the interaggregate pores or macropores starts to decrease. So, these things we will learn later on when we will talk about the swelling potential and swelling pressure of the soil. Talking about the fabric units of the hierarchy, the single unit layer are the smallest, then there will be particles which will be stakings of n unit layers, and then there will be clusters. So, the fabrics hierarchy are the single unit layers are the smallest, single unit layers are this one, then will be the particle staking like this one, and then the cluster are there. So, when the soil starts to or the montomolite starts to absorb moisture, this interlaminar pore space will increase because the water will be absorbed in here. As the interlaminar pore space will increase, the volume of this clay cluster will increase. As the volume of the clay cluster will increase, the inter-aggregate pores or the macro pores will starts to decrease. And finally, all this cluster will occupy this intra-aggregate pore space. And finally, when the swelling is completed fully, then at that point the intra or inter-aggregate pore or macro pore will be the lowest or will be the minimum one, or it will decrease in its volume. Then we will talk about the different properties of different minerals. First, I will talk about the swelling potential. As we already learned that swelling potential is defined as the percentage increase in the volume of a soil when it is inundated with a liquid or it is submerged in a liquid under a minimum surcharge load of 4.9 kPa. So, for example, here we take a soil sample, this is the initial state of the soil sample, then we will submerge this soil in a liquid. This liquid can be water or any salt concentration. Once we submerge this soil into a liquid, the volume of the soil will starts to increase. If we confine the soil laterally, that means if we do not allow the diameter of the soil to change, then in that case there will be change in the height of the soil sample. Let that change in the height will be del H. The ratio between the del H by H is known as the swelling potential of a soil sample. The swelling potential of a soil sample is directly depends on the thickness of the diffuse double layer. So, any factors which controls the diffuse double layer thickness also controls the swelling potential of the soil sample. If we compare the swelling potential of two different clay, say for example montomolite and kaolinite, we could get the different behavior between these two minerals. Say for example, if we plot a relationship between the percentage swell and the maximum dry density for these two minerals, we could see here that the montomolite will exhibit a higher swelling potential in comparison to the kaolinite mineral. The swelling will be highest for montomolite in comparison to kaolinite. This high swelling capacity of the montomolite will be due to the formation of the diffuse double layer with the water, whereas for kaolinite it will not be able to form the diffuse double layer, and mostly its properties will be controlled by its fabrics. So, therefore, the swelling of kaolinite will be very less in comparison to the montomolite. Now, if we compare the swelling potential with the compaction energy, we could see here that for the same compaction energy, the montomolite will swell to a higher value in comparison to the kaolinite, and with the increase in the energy, the difference between their swelling tendency will keep on increasing. So, again this difference in the swelling properties of these two minerals are because of the behavior of mineral. Say for example, due to the formation of the diffuse double layer thickness, the montomolite will be swelling to a higher value, whereas for this one, since the diffuse double layer will not be developed, so its swelling capacity will be very less. Now, if we compare the swelling potential of montomolite in presence of different salt concentration, we could see a different trend. As we know that the swelling potential of soil is controlled by the diffuse double layer thickness. So, the factors which controls the diffuse double layer thickness also controls the swelling potential. Here we could see the effect of salt concentration and the type of salt, say for example, whether it is a monovalent or divalent on different montomolite. In this case, two different montomolite, sodium montomolite and calcium montomolite has been taken, and it has been studied at different salt concentration for two different salts to see their swelling behavior. Here we could see that with the increase in the salt concentration, the swelling potential of both the monomer is decreasing. However, the swelling potential of the sodium monomer is decreasing to a large extent in comparison to the calcium monomer. And also for sodium chloride solution, the monomer will exhibit a higher value of swelling potential in comparison to the calcium chloride solution of the similar concentration. And also when we compare for different salt concentration, we could see here that at low concentration, the difference between the swelling potential between the sodium and calcium monomer is quite large. However, this difference is keep on decreasing with the increase in the salt concentration. So, this again due to the thickness of the diffuse double layer. As we know that the diffuse double layer thickness is proportional to the valency of the cation and it is proportional to the square root of this salt concentration. So, therefore, any change in the salt concentration as well as the valency of the cation also changes the diffuse double layer thickness and consequently the swelling potential. And if we compare the sodium monomer and calcium monomer, the sodium monomer will have a higher value of diffuse double layer thickness in comparison to calcium monomer. Therefore, the swelling potential of sodium monomer will be higher in comparison to the calcium monomer. Now, if we take the amount of monomer in a soil, say for example, if we take a soil mixture containing monomer or an expansive soil and a non-expansive soil, then we could see that with increase in the monomer content in the mixture will increase the swelling potential. This is because if we take or if we consider a solid matrix, soil solid matrix, and if we take a different amount of monomer or expansive soil here, this is the sand grains which is a non-expansive type and this is a monomer or expansive soil. With increase in the expansive soil content or the monomer content, it will starts to fill this void space. As it starts to fill the void space, it will start to push the non-expansive soil in the upward direction. So, that will be manifested as the swelling behavior of the soil. As we increase the monomer content over here, it will push the non-expansive soil more in the vertical direction and more will be the swelling. However, at low monomer content, it may not be able to completely fill this void space or the intra-aggregate pore space or the macro pores. Therefore, the swelling will be very less for a less amount of monomer or expansive soil content. However, when we keep on increasing the monomer content, it will gradually starts to fill this macro pores and then it will start to push the soil in the upward direction. Therefore, the swelling will keep on increasing. So, here we can see this initially the swelling is quite less, but once it completely fills the void space, the swelling increases significantly over here. And depending on the swelling tendency of this expansive soil, say for example, whether it is a high swelling soil or low swelling soil, the fraction of monomer content after which the swelling is increasing significantly also changes. For a high swelling bentonite or high swelling monomer, say for example, in this case around 30 to 40%, there is a significant rise in the swelling potential. However, for a low swelling bentonite, it requires a large fraction of the monomer content or expansive soil content to fill these voids and then increase its volume to a quite extent. Therefore, the swelling potential not only depends on the salt concentration, it also depends on how much of the expansive soil mineral is present in a soil. So, here we can say that the swelling potential of a soil increases with increase in the monomer content in the soil, and after it completely fills this void space or the inter-aggregate pore space, then the volume increase takes place quite rapidly. Next, I will discuss about the swelling pressure. As the swelling pressure, we already know that is the pressure required to prevent the volume change of an expansive soil. Say for example, in this case we will take an expansive soil and we will restrain it in lateral direction, that means we will not allow to change its diameter. Then we will allow this soil to absorb moisture. Due to this moisture absorption, the volume of the soil will try to increase. Now we will apply additional load or overburden pressure to prevent the soil from being increased in its volume. So the maximum pressure which we require here to prevent the soil from increase its volume is known as the swelling pressure. So by definition, the swelling pressure of a sample is defined as the external pressure required to prevent the swelling of a compacted laterally confined sample after soaking in liquid. It also can be defined as the external pressure required to compress a swollen laterally confined soil to its original volume. So going by the second definition, if we allow the soil sample to increase in its volume, and if the volume increases up to this extent, then the amount of pressure which we will be adding in the vertical direction to bring back the volume of the soil to its initial volume is known as the swelling pressure. Similar to the swelling potential, swelling pressure is also proportional to the diffuse double layer thickness. Therefore, if we look into the two mineral over here, montomonite and kaolinite, and if we compare the swelling pressure for those two minerals and compacted at different energy, we could see here the montomonite will have a higher value of swelling pressure in comparison to kaolinite compacted at a same level of energy. Again, this higher value of swelling pressure of the montomonite is because of its ability to form the diffuse double layer thickness with water, whereas the kaolinite possesses less value of diffuse double layer thickness. Therefore, its swelling pressure is also quite less in comparison to the montomonite mineral. Similar to the swelling potential, if we compare the effect of salt concentration as well as the valency of the cations as well as the type of montomonite, we could see the difference in the swelling pressure for different type of mineral at different salt concentration. If we compare all these plots, here we can see that with increase in the salt concentration, the swelling pressure of the montomonite is decreasing. This is because of the decrease in the diffuse double layer thickness with the increase in the salt concentration. As we know that diffuse double layer thickness is inversely proportional to the salt concentration, that means higher is the concentration, lower is the diffuse double layer thickness, and lower is the diffuse double layer thickness, lower will be the swelling tendency. Therefore, lower will be the swelling pressure. That is why the swelling pressure of the montomonite is keep on decreasing with increase in the salt concentration. This trend can also be observed for the calcium montomonite mineral. However, again if we compare the swelling pressure at different concentration, we could see a decrease in the value of swelling pressure with increase in the concentration. That means at low concentration, the difference between the swelling pressure for calcium montomonite and sodium montomonite is quite high, but with increase in the salt concentration, that difference keep on decreasing, and at very high concentration they comes to a very close value. Again, if we compare the salt effect, the type of valency effect on the swelling pressure for the same montomonite, we could see here that montomonite with sodium salt will have a higher value of swelling pressure in comparison to the calcium salt. That is because again we know that diffuse double layer thickness is inversely proportional to the valency of the cation. Higher is the valency, the lower will be the diffuse double layer thickness. So, therefore, the diffuse double layer thickness will be less for calcium chloride in comparison to the sodium chloride. As the diffuse double layer thickness is less for calcium chloride, the swelling pressure of the soil will also be less. And if we compare the swelling pressure between sodium montomolnite and calcium montomolnite, we could see the sodium montomolnite will be having a higher value of swelling pressure in comparison to calcium montomolnite for the same concentration and same type of salt. So, here we can conclude that the swelling pressure of soil sample of calcium montomolnite and sodium montomolnite decreases with increase in the salt concentration. Again, the swelling pressure is not only depends on the salt concentration, but it also depends on the type or the valency of the cations of the pore fluid. Higher is the cation valency, lower will be the diffuse double layer thickness and lower will be the swelling pressure. And similarly, the sodium montomolnite will have a higher value of swelling pressure in comparison to the calcium montomolnite for same concentration and same type of salt solution. Next, we will see the effect of expansive soil content on the swelling pressure. With increase in the bentonite or montomolnite content, the swelling pressure is keep on increasing. Here in this case, we have taken two different type of swelling soil, a low swelling and high swelling soil. If we compare both the swelling soil, we can see here after a certain fraction of the bentonite content or the montomolnite content, the swelling of or the swelling pressure of the mixture containing high swelling bentonite increases rapidly, whereas for low swelling bentonite it needs a higher fraction of bentonite content to increase its swelling volume. This is because again the packing phenomena, like if we take the montomolnite, a higher swelling bentonite requires low amount of bentonite or montomolnite content to completely fill this intra-aggregate pore space or the macropores, and then once it fills the macropores, then it starts to push this non-expansive soil particles in the upward direction, thereby increasing its swelling pressure. Whereas a low swelling bentonite or low swelling montomolnite requires a higher amount of montomolnite content to completely fill this macropores to push this non-expansive soil in the upward direction. Therefore, it requires a higher bentonite content to increase its swelling pressure significantly. Next, I will discuss about the hydraulic conductivity of different minerals. Hydraulic conductivity is defined as the rate of flow of liquid through a soil. Higher is the hydraulic conductivity, faster is the rate of flow of the water inside the soil. And this hydraulic conductivity depends on the diffuse double layer thickness as well as the fabric of the structure, whether that is a flocculated structure or a dispersed structure. Now, if we compare the hydraulic conductivity of different minerals, we could see here the kaolinite has a higher value of hydraulic conductivity, and it is in between in the range of 10 to the power minus 7 to 10 to the power minus 9 meter per second, whereas the montomolnite will have the lowest value of hydraulic conductivity, which will be in the range of 10 to the power minus 9 to 10 to the power minus 11 meter per second. The low value of hydraulic conductivity for montomolnite will be because of its diffuse double layer thickness, whereas the high value of hydraulic conductivity for kaolinite will be because of its non-able to form the diffuse double layer thickness and because of its fabrics, which will be mostly flocculated one. So, therefore, the kaolinite will have a higher value of hydraulic conductivity in comparison to montomolnite and illite. Now, we will try to understand the diffuse double layer thickness and its influence on the hydraulic conductivity. Say for example, here we will take a montomolnite particles or an expansive soil mineral. If we look into this mineral, it will absorb moisture. Now, this moisture can be divided into different types, say for example adsorbed water and diffuse double layer water. And beyond this diffuse double layer water, this water is known as free water, and this thickness is known as the diffuse double layer thickness. Here we can see, in this case the thickness of the diffuse double layer is quite less. So therefore, there will be a large amount of space available for the free water. Now free water can move freely due to gravity. As the amount of free water is more here, the free water can freely move, and therefore the hydraulic conductivity will be high here. But if we take a mineral with a larger value of diffuse double layer thickness, here we can see the two diffuse double layer thickness are overlapping here, and as the diffuse double layer water is immobile water, as it will not move freely, it will restrict the free movement of the free water here. As the no free water is available here, the water cannot flow through this. Therefore, the hydraulic conductivity of this will be very low. So therefore, we can conclude here that higher is the K value, that means lower will be diffuse double layer thickness or vice versa, and lower will be K value or the hydraulic conductivity, higher will be the diffuse double layer thickness. If we compare the different minerals, the diffuse double layer thickness will be different. Therefore, the hydraulic conductivity of these three minerals will also be different. Now, if we compare the hydraulic conductivity at different void ratio for montomonite, illite and kaolinite, we will get a trend like this. Now, if we compare the hydraulic conductivity at a particular void ratio, we could see here the montomonite will have a very low value of hydraulic conductivity in comparison to illite and kaolinite, and kaolinite will have a very high value of hydraulic conductivity in comparison to the other two minerals. Again, the lower value of hydraulic conductivity of montomonite will be due to its formation of the diffuse double layer thickness or its higher diffuse double layer thickness in comparison to the illite and kaolinite. Since the kaolinite will not be able to form the diffuse double layer thickness, its hydraulic conductivity will be very high and it will be more pervious in comparison to the montomonite and illite. If we compare the hydraulic conductivity of different minerals in the presence of different pore fluid, we could see the different trends here. Say for example, in this case we have taken montomonite and illite, and the hydraulic conductivity has been compared for water, ethyl alcohol and carbon tetrachloride. So here we could see that for montomonite, with increase in the salt, the hydraulic conductivity is keep on increasing. We know that water has a higher value of dielectric constant in comparison to ethyl alcohol and carbon tetrachloride. CCl4 has a least value of dielectric constant, and since the dielectric constant is very less here, the diffuse double layer thickness will also be very low in this case. As the diffuse double layer thickness is very less, the amount of diffuse double layer water will also be low and the free water will be very large. So therefore, the hydraulic conductivity of this will be maximum. But on the other hand, for soil sample with water which has a higher value of the dielectric constant, the diffuse double layer thickness will be quite large and therefore, the hydraulic conductivity will be very less. Now, if we compare between sodium montomonite and calcium montomonite, because of this calcium is an exchangeable cation, the diffuse double layer thickness in this case will be less in comparison to the sodium montomonite. Therefore, although the dielectric constant is same, that means both case water, the hydraulic conductivity for calcium montomonite will be higher in comparison to the sodium montomonite. Now, if we compare this behavior with the illite mineral, we could see here that the same trend is also existing between the different pore fluid. Again, with decrease in the dielectric constant, the hydraulic conductivity is keep on increasing. The illite mineral will be having the lowest value of hydraulic conductivity in the presence of water in comparison to the ethyl alcohol and carbon tetrachloride. And if we compare with the montomonite, we could see here the difference in the hydraulic conductivity will be quite large for montomonite in comparison to illite. This is because of the large effect of the dielectric constant on the diffuse double layer thickness for montomonite. Since the diffuse double layer thickness is not so large for illite, the effect due to a stiff decrease in the dielectric constant is not that much prominent for illite in comparison to the montomonite. If we compare between montomonite and kaolinite, we could see that the effect of dielectric constant is very less for kaolinite mineral. Here if we compare, by decreasing the dielectric constant from water to carbon tetrachloride, there is a significant increase in the hydraulic conductivity of montomonite. However, in this case, this change in the hydraulic conductivity is not that significant. This is because of the hydraulic conductivity in this case is not controlled by the diffuse double layer thickness. In this case, or in the kaolinite mineral, the hydraulic conductivity is controlled by its fabric. As we decrease the dielectric constant, the net attractive forces between the particles will increase, and that will leads to a flocculated structure. As the structure becomes flocculated, the hydraulic conductivity will increase. So, therefore, here we can see the hydraulic conductivity is increasing from the water, and that increase is quite not that significant in comparison to montomonite and illite, and this increase in the hydraulic conductivity is because of its flocculated structure. Since the hydraulic conductivity is controlled by the diffuse double layer thickness, and the diffuse double layer thickness gets also affected by the salt concentration. If we plot a graph between hydraulic conductivity and void ratio for montomonite at different salt concentration, we could see the effect of salt on the hydraulic conductivity. We could see here with the increase in the salt concentration, the hydraulic conductivity also increases. This increase in the hydraulic conductivity with increase in the salt concentration is due to the decrease in the diffuse double layer thickness. Since the diffuse double layer thickness gets decreased with the increase in the salt concentration, the hydraulic conductivity also gets increased due to a increase in the salt concentration. So, here we could see the hydraulic conductivity is increasing to a large extent due to an increase in the salt concentration from 0 to 1 n of sodium chloride. Now, if we look into the effect of presence of expansive soil in a soil matrix, then we will see that with increase in the montomonite content or expansive soil content, the hydraulic conductivity will keep on decreasing. Here we can see in the dry state, these are the solid non-expansive soil, say for example sand grains, and these are the expansive soil particles. This is in dry state. So, there will be large amount of macropores or interaggregate pores. As we allow this montomonite or expansive soil to absorb moisture, then its volume will starts to increase. At the volume of this soil starts to increase, this will starts to occupy the space between the individual grain particles, or it will starts to fill this macropores. As it starts to fill the macropores, the hydraulic conductivity will starts to decrease. Therefore, as we gradually increase the montomonite content, we could see there is a drop in the hydraulic conductivity or there is a decrease in the hydraulic conductivity. So, this decrease in the hydraulic conductivity due to increase in the montomonite content is due to the filling of this pore space by the expansive soil present over here. And after certain value, once it fills the voids completely, there will be a marginal decrease in the hydraulic conductivity in comparison to the less montomonite content state. So, here we can see two different montomolites has been taken. One is a calcium montomolite, another is a sodium montomolite. Sodium montomolite is a very high swelling soil in comparison to calcium montomolite. Therefore, for the same fraction or same increase in the montomolite content or the expansive soil content, the change in the hydraulic conductivity is quite different. For the same amount of expansive soil content, for example 5% of sodium montomolite content and 5% of calcium montomolite content, we could see a lower value of hydraulic conductivity for sodium montomolite in comparison to calcium montomolite. Similarly, here also we could see a lower value of hydraulic conductivity for sodium montomolite in comparison to the calcium montomolite. Since the swelling ability of sodium montomolite is more in comparison to calcium montomolite, the calcium montomolite can effectively fill this void space even at lower montomolite content. Therefore, at low montomolite content, the sodium montomolite exhibits a lower hydraulic conductivity in comparison to the calcium montomolite content. Here we can see the SEM analysis of soil matrix. At 10% montomolite, we could see some of the opening space or the macropores over here. But as we increase the montomolite contents, this void space starts to get filled by the expansive soil. Here we cannot see any macropores, or all these macropores are filled by the expansive soil. And once these macropores are filled by the expansive soil, the hydraulic conductivity gets decreased to a large extent. So, here the graph has been plotted between the hydraulic conductivity and void ratio for the expansive soil mixture with different content of expansive soil. This is the 100% expansive soil, that is maybe 100% of montomolite, and this is the 5% of montomolite. Here we can see a very low value of hydraulic conductivity for an expansive soil. As we decrease the expansive soil content, the hydraulic conductivity is keep on increasing, or if as we increase the expansive soil content, the hydraulic conductivity is keep on decreasing. So, again this decrease in the hydraulic conductivity due to the increase in the expansive soil content is because of the ability of expansive soil to fill those voids completely and prevent the migration of the water, therefore, a decrease in the hydraulic conductivity. If we compare the effect of compaction effort on the hydraulic conductivity, we could see that if we compact a soil sample with a low effort, then the hydraulic conductivity will be quite high. If we compact a soil with a high effort, then the hydraulic conductivity will be quite less. So, this is quite evident from here that with increase in the compactive effort, the hydraulic conductivity of the soil gets decreased. However, the maximum difference in the compactive effort could be seen on the dry side of the OMC in comparison to on the wet side of the OMC. On the wet side, we could see the difference in the hydraulic conductivity is quite less for all these three compaction effort. The difference in the hydraulic conductivity on the dry side of the OMC because of the compactive effort is due to its fabric. Mostly in dry side, the fabric is flocculated, therefore, the hydraulic conductivity is significantly high, and at low effort a large amount of pore space will be present here which could not be broken into, therefore, the hydraulic conductivity will be high. But with increase in the compactive effort, the flocculated structure can be broken into, and therefore, the hydraulic conductivity will be less here. Next, I will discuss about the compressibility behavior. The compressibility behavior of a soil primarily depends on the contact stress or the effective stress principle. Here we can see two clay plates, and there will be the forces of repulsion, forces of attraction, there will be the contact stress as well as the pore water pressure. So, when we apply a load PT, that will be taken by the PC, which will be the contact pressure, the pore water pressure, the repulsive pressure between the clay plates, and the attractive pressure between the particles. In equilibrium state, PT will be equals to PC plus U plus R minus A, or the contact pressure PC will be equals to PT minus U minus R plus A. Now, if we take in expansive soil, then the particles to particle separation will be quite large. So, there will be no contact pressure between the particles, and therefore, the total pressure will be taken up by the attractive and repulsive pressure. Since fully saturated state, U will be equals to 0. So, PT will be equals to R minus A. So, therefore, any reduction in the repulsive pressure will increase the contact pressure or the effective stress. The compressibility of a soil will be increased with the decrease in the salt concentration, the decrease in the valency of the cation, the increase in the pH, the increase in the specific surface area, increase in the dielectric constant, and increase in the temperature. Since all this factor will increase the repulsive pressure, therefore, the compressibility of the soil will increase with all this factor. Now, if we look into the compressibility of soil, then the compressibility will be governed by two mechanisms, mechanism 1 and mechanism 2. In mechanism 1, the volume change of the soil is primarily controlled by the shear resistance at the near contact points, and the volume change occurs by the shear displacement or by the sliding between the particles or both. And at equilibrium, when the shear stress becomes equals to the shear strength, which is controlled by the effective stress. In mechanism 2, the compressibility behavior will be controlled by the diffuse double layer thickness, and in this case the volume change is primarily governed by the long range electrical repulsive forces, which is double layer in nature, and the equilibrium takes place when this sum of this self weight of the solid particles and the attractive forces, which is becomes equals to the repulsive pressure between the particles. So, if we look into different clay mineral, the mechanism 1 or mechanism 2 can govern their compressibility behavior. If we look into the three minerals montomonite, illite and kaolinite, we could see the difference in the compressibility behavior in the presence of different pressure. We could see the montomonite will be exhibiting a higher value of void ratio in comparison to illite and kaolinite. The compressibility behavior of montomonite is governed by the second mechanism, that means it will be controlled by the diffuse double layer thickness, whereas for kaolinite, which will not be able to form the diffuse double layer thickness, its compressibility behavior or volume change behavior will be controlled by the first mechanism, that is because of its shear resistance at the near contact points. And if we look into these three different mineral, we could see the montomonite can be compressed to a higher extent in comparison to illite and kaolinite. If we look into the compression index of montomonite, generally this is between in the range of 1 to 2.6, illite is between 0.5 to 1.1 and kaolinite is between 0.2 to 0.3. That means the kaolinite is less compressible in comparison to montomonite because of the mechanism which are quite different for kaolinite in comparison to montomonite. So, here we could see that due to the formation of the diffuse double layer, montomolinite exhibits a higher void ratio in comparison to kaolinite at lower pressure, and with increase in the pressure the montomolinite will get more compressed in comparison to the kaolinite because of the compression of the diffuse double layer thickness, whereas in this case the particle fabrics will prevent the kaolinite particles to compress to a large extent. Therefore, the compressibility of kaolinite will be less in comparison to the montomolinite. Since the diffuse double layer thickness gets affected by the different salts or the dielectric constant, if we change the pore water in the soil, we could see the different compressibility behavior of montomolinite. Similarly, we could see also the different compressibility behavior of kaolinite. Since the compressibility of montomolinite is affected by or controlled by the diffuse double layer thickness, here we could see with decrease in the dielectric constant, the diffuse double layer thickness gets decreased. Therefore, the compressibility of montomolinite will also gets decreased. And if we compare the void ratio at a given pressure, we could see montomolinite with water will have a higher value of void ratio in comparison to ethanol, acetone or CCl4. Since CCl4 have a lower value of dielectric constant, the void ratio of montomolinite in the presence of CCl4 will be least out of these 4 cases. But if we compare with the kaolinite, we could see the difference in the presence of all these 4 pore water has a marginal effect on kaolinite in comparison to montomolinite, because in kaolinite it is not controlled by the diffuse double layer thickness. In fact, it is controlled by its fabrics. As we increase the or as we decrease the dielectric constant, the net attractive forces will decrease, the net attractive forces will increase. As the net attractive forces will increase, the particle will becomes more flocculated. So, therefore, here we could see the CCl4 will be more flocculated, therefore, it will have a larger void ratio in comparison to water, and it will be in a reverse trend in comparison to montomolinite. That means, in montomolinite the decreasing trend in the void ratio will be water, ethanol, acetone and CCl4, whereas for kaolinite the decreasing trend in the void ratio at any pressure will be like first CCl4, that means CCl4 will be the highest void ratio comparison to acetone, then comparison to ethanol, then comes the water. This is because the formation of the flocculated structure here. Since the flocculated structure will have a larger void ratio, therefore, kaolinite with a CCl4 will have a higher value of void ratio in comparison to water. So, here we can conclude the compressibility behavior of montomolinite is controlled by the diffuse double layer thickness. For kaolinite, with the decrease in the dielectric constant, the net attractive forces increases and hence the resistance against the compression also increases. And due to the formation of the flocculated structure, the kaolinite mineral in the presence of a low dielectric constant pore fluid will have a higher value of void ratio comparison to a pore fluid with a higher value of dielectric constant. Similarly, if we compare the type of exchangeable cations present in a montomolinite with the compressibility behavior, we could see that with increase in the valency of the exchangeable cation, the compressibility behavior of the montomolinite will decrease. Say for example, if we compare with sodium, calcium and aluminum, since sodium is a monovalent, calcium is divalent and aluminum is trivalent, with increase in the valency of the exchangeable cation, the compressibility behavior is decreasing. This because of the decrease in the diffuse double layer thickness. Now, if we compare between sodium and lithium, since the lithium has a lower size comparison to sodium, it will have a higher diffuse double layer thickness in comparison to sodium. Therefore, it will have a a higher value of void ratio in comparison to the sodium monotomolite. Hence, we can say that the compressibility behavior will decrease with valency and with size of the ion or cation. Now, if we compare the compressibility behavior of monotomolite in the presence of different pore fluid, we could see that with decrease in the dielectric constant, the diffuse double layer thickness is decreasing, and therefore, the compressibility behavior also changing. That means, the monotomolite with a lower value of dielectric constant will have a lower value of void ratio in comparison to a higher value of dielectric constant. So, here we can say that the compressibility decreases with decrease in dielectric constant of monotomolite, dielectric constant of the pore fluid present in the monotomolite. If we compare with the salt concentration, here we can see with increase in the salt concentration, the compressibility of the monotomolite is decreasing. Again, this decrease in the compressibility behavior due to increase in the salt concentration is due to the decrease in the diffuse double layer thickness. Now, if we compare with the compression index of kaolinite and non-expansive and expansive soil matrix, then we can see here an expansive soil, say for example bentonite, will have a high value of compression index in comparison to the kaolinite. This is because of the formation of the diffuse double layer thickness. Now, if we add non-expansive soil to bentonite or to an expansive soil, then the compressibility of the soil it's keep on decreasing over here, and it becomes almost identical at very low amount of expansive soil content. If we look into the kaolinite here, the compression index is getting, it's almost identical and it's not get affected significantly in presence of different pressure, and it will be very low in comparison to an expansive soil, say for example monotomolite. But if we look into the effect of salt on compression index on bentonite or monotomolite, we could see here with increase in the salt concentration, the compression index of the soil is decreasing. That means, the tendency of a soil to get compressed is decreasing with increase in the salt concentration. So, this decrease in the compression index or decrease in the compressibility of the soil due to increase in the salt is because of the reduction in the diffuse double layer thickness. Whereas, if we look into the kaolinite over here, the kaolinite is marginally affected with the increase in the salt concentration, because here it is not getting affected on its diffuse double layer thickness, since it is not able to form the diffuse double layer. Therefore, the kaolinite is less or least affected in the presence of salt concentration in comparison to the bentonite. Next, I will talk about the coefficient of the consolidation. The coefficient of consolidation, which is generally denoted by the term Cb, indicates the rate of consolidation. Higher is the Cb value, the faster will be the rate of consolidation, and the consolidation will take place quickly. Now, if we compare the Cv value or the coefficient of the consolidation value for different minerals, we could see here that the mineral monotomolite will have a very low value of coefficient of consolidation in comparison to kaolinite and illite. And out of these three minerals, the kaolinite will have a highest value of coefficient of the consolidation. the higher value of coefficient of consolidation for kaolinite will indicate a faster rate of consolidation for any pressure. Similarly, if we compare with sodium monomerlite and the calcium monomerlite, we could see the calcium monomerlite will have a higher value of coefficient of consolidation in comparison to the sodium monomerlite, and that indicates the calcium monomerlite will consolidate faster in comparison to the sodium monomerlite. So, here we can conclude here the sodium monomerlite has a lower value of Cb indicating a slower rate of consolidation, and kaolinite has a higher value of Cv indicating a faster rate of consolidation. If we take monomerlite and if we compare with the different exchangeable cations present over here, then we could see here with increase in the valency of the exchangeable cation present in the monomerlite, the coefficient of the consolidation is increasing. That means, with increase in the valency of the exchangeable cations, the rate of consolidation is also increasing. The Fe monomerlite will consolidate faster in comparison to the calcium monomerlite and the sodium monomerlite for any given pressure. Since the coefficient of the consolidation is affected by the diffuse stable layer thickness or is controlled by the diffuse stable layer thickness, and the liquid limit is also controlled by the diffuse stable layer thickness, a correlation between the coefficient of the consolidation and the liquid limit can be expected. Therefore, when we plot the relationship between the coefficient of the consolidation and liquid limit, we could see a linear trend over here. That means, with decrease in the liquid limit of the soil, the coefficient of consolidation it is keep on decreasing. That means, higher is the liquid limit, higher will be the diffuse stable layer thickness, therefore, the lower will be the coefficient of the consolidation or lower will be the rate of consolidation. Similarly, if we look into the plasticity index and the coefficient of the consolidation, again we could see a decreasing trend. That means, with increase in the plasticity index, the coefficient of the consolidation of the soil is also decreasing. Therefore, higher is the liquid limit and plasticity index, lower will be the coefficient of the consolidation and slower will be the rate of consolidation of a soil sample. Now, if we look into the effect of different pore fluid on the coefficient of the consolidation, we could see here this is in presence of the water for kaolinite and monomerlite and illite. In water, the kaolinite will have a higher value of coefficient of consolidation in comparison to the sodium monomerlite, whereas sodium monomerlite will have a least value of the coefficient of the consolidation. But if we change the pore fluid from water to carbon tetrachloride, here the dielectric constant is around 80 and here it is around 4. If we decrease the dielectric constant, we could see a reverse trend over here. That means, the kaolinite's coefficient of the consolidation will not change that much, but on the other hand, the coefficient of the consolidation of sodium monomerlite will increase to a significant extent. So, this change in the coefficient of the consolidation for sodium monomerlite is because of the collapse of the diffuse stable layer thickness or significantly decrease in the diffuse stable layer thickness in the presence of CCl4. As the diffuse stable layer thickness reduces significantly, the individual particles can come closer and the repulsive pressure between these particles will decrease. Therefore, the rate of consolidation will also decrease to a large extent. The presence of the salt affects the Cv of kaolinite marginally. However, the monomerlites get affected significantly. That is because of the significant influence of CCl4 on the diffuse stable layer thickness of monomerlite. If we compare the coefficient of the consolidation of monomerlite in presence of different concentration of sodium chloride solution, we could see here with increase in the salt concentration, the diffuse stable layer thickness will decrease. As the diffuse stable layer thickness will decrease, the coefficient of the consolidation will keep on increasing. That means, the rate of consolidation will increase with increase in the salt concentration. So, therefore, the CV will increase with the increase in the salt concentration of the pore fluid. Now, we can see the effect of different mineral on coefficient of volume change. The coefficient of volume change is defined as the compression of the clay layer per unit original thickness due to unit increase in the pressure. The coefficient of volume change is defined as the compression of the clay layer per unit original thickness due to a unit increase in the pressure, and it can be defined as del E by del sigma divided by 1 plus E. Now, if we compare the MV value between these three minerals at different pressure, we could see here the MV for kaolinite is quite less in comparison to illite and montmolite, and montmolite will have a higher value of volume change behavior in comparison to kaolinite. That means, at any increase in the pressure, the montmolite volume change will be quite high in comparison to kaolinite. The least value of compressibility or coefficient of volume change of MB because of its flocculated structure, which will prevent the kaolinite particles to decrease in its volume to a large extent due to increase in the pressure. Since the montmolite compressibility is governed by the diffuse double layer thickness, with increase in the pressure, the diffuse double layer gets reduced, and therefore, the coefficient of the volume change will increase to a large extent in comparison to the kaolinite mineral. Next, we will discuss about the shear strength behavior of the three minerals in the presence of different salt. The shear strength and the normal pressure plot has been plotted for kaolinite and bentonite in the presence of different mineral. Here we can see for the kaolinite, with decrease in the dielectric constant, the shear strength of the soil is increasing. Similarly, if we look into for montmolite mineral, with the decrease in the dielectric constant of the pore fluid, the shear strength of the soil is decreasing. But if we compare these two, we could see here change in the shear strength is quite narrow range, whereas for kaolinite a significant change has been noticed. This change in the behavior or the shear strength between kaolinite and bentonite, again because of their way of arrangement or the net diffuse double layer thickness. Since for kaolinite the fabrics control its behavior, with decrease in the dielectric constant, the net attractive forces will keep on increasing, and as net attractive forces keep on increasing, the structure becomes more flocculated, and therefore, the shear strength will be more. As the kaolinite will be more flocculated with the decrease in the dielectric constant, the shear strength of the flocculated kaolinite will be more in comparison to the kaolinite with a less amount of flocculated structure. On the other hand, if we compare for bentonite, the lower value of shear strength of bentonite in comparison to kaolinite is due to its repulsive pressure, which is reduces the net attractive pressure. So, therefore, if we compare the shear strength between bentonite and kaolinite, the kaolinite will have a higher value of shear strength in comparison to the bentonite. So, this higher value of shear strength for kaolinite is because of the increase in the net attractive forces, which results in the flocculation tendency and therefore, increase in the shear strength. Now, if we compare the undrained shear strength of kaolinite and montmolite, we could get this plot. Now, if we compare the undrained shear strength of kaolinite and montmolite for any void ratio or any water content, we could see that kaolinite in the presence of CCl4 has a higher value of undrained shear strength in comparison to water. That means, with a decrease in the dielectric constant, the undrained shear strength of kaolinite is increasing. But if we compare the same behavior for montmolite for any void ratio in the presence of water or CCl4, we could see a reverse trend. That means, with decrease in the dielectric constant, the shear strength of monotonite is decreasing. So, this can be attributed again to the formation of the diffuse stable layer and the fabrics between this kaolinite and monotonite. The undrained shear strength of kaolinite depends on the net attractive forces and the particle arrangement. With the decrease in the dielectric constant from here to here or increase in the salt concentration, the interparticle attractive forces of kaolinite particles will increase. With this increase in the net attractive forces, the flocculated structure will be developed. As the flocculated structure will be developed, and therefore, its shear strength will increase. Now, if we look into the monotonite, here the shear strength will be controlled by the diffuse stable layer thickness. We know that diffuse stable layer water is a more viscous one. Therefore, higher is the diffuse stable layer water, the viscous shear resistance to resist the shear formation will be more. With a decrease in the diffuse stable layer thickness, the viscous diffuse stable layer water will also decrease. Therefore, its viscous shear resistance to resist the shear deformation will also decrease. Therefore, we can see here, with a decrease in the dielectric constant from water to CCl4, the diffuse stable layer thickness gets reduced. Therefore, the viscous water present in the soil also gets reduced. So, therefore, the viscous resistance to resist the shear deformation will reduces, which results in a reduction in the undrained shear strength of the monotonite particles. Therefore, the behavior of kaolinite and monotonite particles due to a reduction in the dielectric constant are quite reverse. So, these are the summary of the lectures, and these are the different references which has been used to prepare this lecture, and thank you very much.